Welcome to Industry Ignited, the podcast where we spotlight the leaders, innovators, and disruptors shaping the future of industry. I'm your host, Dr. Leanne Aguilar, and today we're diving into the world of engineering design, advanced analysis, and product development with someone who has made a career out of solving the kind of technical challenges most people would call impossible. My guest today is Andy Johnston, PE, Principal Mechanical Engineer at Johnston Engineering, a licensed professional engineer in Washington State, and an instructor of mechanical engineering at Gonzaga University. With over 20 years of expertise in product development, mechanical engineering design, and physics-based engineering analysis, Andy is a recognized subject matter expert in thermal management, two-phase flow, and heat transfer, critical areas for industries ranging from biotechnology and renewable energy to aerospace and advanced manufacturing. In our conversation today, we'll explore Andy's journey into engineering entrepreneurship, the innovation process at Johnston Engineering, and how they apply advanced analysis to solve tough problems, and the trends shaping the future of engineering and product development. Andy, welcome to the show.
Thank you for having me.
We're glad to have you. So Andy, you've spent over 2 decades in mechanical engineering and product development. Can you take us back to the start of your career and what first drew you into this field?
Sure, yeah. So growing up, I would always be interested in how things went together, how things were made. I would take things apart and try my best to put things back together. But taking apart motors, just making kind of a mess out of things that I would have access to, and just really being curious about how things were made. I went to Gonzaga and got my bachelor's in mechanical engineering in 2003. Then I went to work for a company in aerospace, isothermal systems research. Started there in 2004, and so that was military and aerospace electronics cooling and packaging. And so this was packaging of electronics that needed to be in extreme environments, both in cold environments and hot environments. So these are not electronics that can be cooled with air. Like you think about your computer, that you just have a fan that blows air across it. But in aerospace environments, this might be something that is flying at twice as high as an airliner, which is negative 70 degrees C, and then landing in the hottest desert in the world, right? So then when it's on the ground, it would need to be cooled. So air cooling is not an adequate way to cool those kinds of components. And so we would cool it with a non-conductive liquid. And so, there's electronics that are directly in contact with liquid, and we'll be spraying this liquid directly on those electronics and then packaging them very densely. So in aerospace, you need things to be as light as they possibly can, but be strong enough. So there's lots of structural analysis, a lot of weight reduction, a lot of packaging to make sure that things take up the least amount of space, but they have to meet their requirements for the forces they experience during takeoff and landing. So a electronics chassis doesn't become a projectile on a hard landing. So there was lots of structural analysis, lots of fluid flow analysis, and lots of thermal analysis to design those kind of systems. So I worked for isothermal systems research for 5.5 years. I stayed on the military and aerospace side the entire time. But the company took venture capital money, and venture capital money wants to scale. And so they started a commercial division. They scaled up. They had offices, all over the country. And there was 200 approaching 300 employees. I don't think we actually hit 300, but developed a data center product, which was basically spot cooling of servers with multiple CPUs in those servers. They had agreements with HP and Dell. I think the real killer of it was that there was resistance at the data center side. So they developed a product and manufacturing line for a product that had no real market for it. Lots of layoffs, 8 rounds of layoffs. I survived at Isothermal Systems Research until Parker Aerospace purchased us. So, I was I think I was employee 70 at ISR, and we got up to less than 300. And then being part of Parker Aerospace, huge organization. I think there's around 60,000 employees and in the north of $10 billion in revenue. So it's a completely different corporate type of environment. And Parker's objective is really to increase revenue while decreasing cost by focusing on improvements of manufacturability. So I worked for Parker for another 5.5 years, and then Parker was going to close down their location in Liberty Lake and bring everybody back to kind of the mothership back in Ohio. And within about 2 weeks of Parker making that announcement, I started my company. And I was working at nighttime on my stuff. Parker wanted us to stay on and finish our project. So my exit interview with Parker was actually on Halloween. So the end of October of 2005. 2015. And I left that exit interview and I collected on my first invoice that same day. So it was a good start. That was an energy storage project. And then just been slowly working since then and working on more projects, bigger projects and growing since then.
So I hear that your curiosity, your natural curiosity, and the desire to build things and figure out how things work specifically in extreme environments is what I'm hearing is what led to your career and kind of the advancements within your career. And how did those experiences within your career, because I know you have the diversity you mentioned, aerospace, military, clean tech, how did that shape your approach to the engineering you're doing today?
Yeah, there's a lots of different types of jobs that engineers work on and lots of different fields that mechanical engineers work on. But the area where we really work is in creating brand new things. So, these are working on things that are only existing in a fume hood at a national lab, and we need to go and scale those up to something that's more of a lab type proof of concept test, and then we'll go scale it up to something that's much bigger, and then scale it up from there. So, as you go through these processes, we're really trying to learn as quickly as we possibly can from our expert customer that we're working at, right? So we might be working with an expert at a company who's proved it at a small level, or working with a researcher at Pacific Northwest National Labs, which is 2 hours away from us, and they're really experts in their technology that we know nothing about when we start working on that project. And so we need to learn really as quickly as we can, right? They're really good at researching, but they're not as good at doing that scale up into more of a commercialized project. And that's where we work. So, the fact that aerospace is very precise in terms of their requirements to make sure that these systems are safe. And over many years, aerospace has really learned that the cheapest way to get things to market is by doing analysis and simulations on the computer screen. So you fail on the computer screen and you iterate it in with your CAD model, and then you resimulate. So you're doing your physics-based simulations for structures and making sure that things are strong enough. This is forces, torques, pressures, things like that you can simulate how that physically interacts with materials. And heat is keeping heat in or out, or maintaining a process at a certain temperature. Or the fluid flow is really where you're how fluids interact with structures or with each other, right? Those are the kind of things where it's essential for various different industries, and aerospace really forces it into those industries, and they've proven that doing things and developing it that way is the cheapest way to make sure that by the time you're actually building something that is very expensive, that you've built it correctly, and that you've made something that's as safe as it can possibly be, right? So what we've done is we've taken those same softwares that we use. So we use ANSYS for our physics-based simulation. That's the same thing that we were using for simulation at Parker Aerospace. And we're using them in many different industries. So a lot of clean tech, but lots of other industries as well. And then using those kind of simulations, that means that you'd be able to do cheaper development, fail on the computer screen, and then when you get it to market, it's going to work.
Yeah. So when you started Johnston Engineering, was there a specific gap in the market that you identified and wanted to fill? Tell me a little bit about like why you started your company.
It was just me when I started, right? Spent about half the time searching for applicable engineering projects that I could be useful to a customer on, and about half the time doing that kind of work. So in terms of the strategy to go, fill this need, I didn't have the foresight when I first started. I knew that I wanted to be in the driver's seat to where the success or failure really rested on my shoulders. I think that was a lot of drive for it. And I think that anybody who's worked for a large company and sees, there's really good and bad of a large company. There's fantastic access to training and mentors and really cool projects that you get to work on. But there's also some big bureaucracy in big companies and some inefficiencies and decisions that don't make sense, but they're strategic vision type decisions. So I really wanted to be in that driver's seat where I got all the good and the bad of all of those decisions, right? So it started out, working for various different companies. I had a couple analysis projects because really my background is strong analysis. And then some initial consumer products. And it wasn't really until finding that really the match between how important clean technology is to our future economy and understanding that clean tech development has very similar challenges of aerospace because it's brand new technology and it's all brand new areas that need to be discovered. And so we're constantly learning and a lot of the things that we do, we have to be just comfortable not knowing what we're doing, right? It's being comfortable with uncertainty and working through design and analysis to make sure that we reduce those risks. Like, one of our biggest jobs for our customer is to reduce risk so our customers can be technically successful in their scale up. Kind of evolved over time of finding those markets where the right skill set that was first developed in aerospace could be applied to those other markets.
Okay. And yeah, that makes a lot of sense. I never really thought about the connection between like clean energy and the innovation required there and aerospace, but that does make a lot of sense. And considering that you're working in these different industries, how do you adapt your processes to meet the different technical requirements of each?
Yeah. So, there's really 4 areas of service that we provide. And, mechanical engineering and the laws of physics don't change. And so it's really just adapting the services to each different project. So we offer 4 things and we adapt those based on each different project. It's design, analysis, build, and test. So when we're talking about design, we're talking about CAD models, right? So this is we're designing the individual parts, how those individual parts go together into a system. And so you've got a 3D representation of how these things go together. And what's different between different projects is how the specifics interact. So, you can have we have customers, we have like multiple CO2 capture customers, right? And there's similarities between those, but really the difference between those individual customers' intellectual properties is what's different. And so we need to make sure, number one, that we're very careful of other companies' intellectual property, because that and firewalling that from the rest of the world and other people that are not working on that project is very important to us, but making sure that we're designing with their intellectual property in mind. So we design, we then go do analysis. So it's those 3 areas that I told you, which is structural, thermal, and fluid flow. A lot of the clean tech companies need those 3 areas. A lot of structural and thermal, fluid flow depends on the project. Then we build the hardware, right? So we have a network of fabricators. Plus we do some internal fabrication ourselves. We have CNC mills and lathes, CNC turret press, CNC brake, and we do some of that in-house, or a combination if we have our network of fabricators that can do it cheaper or faster or more precise, than we can do it. So we build the entire system and then we make sure that it works. So we start testing testing it. So we're verifying all the components work. We can do very low uncertainty experiments. Some experiments might be like a process recipe, developing like how long should this thing be at this pressure, and then how long should it be at this temperature afterwards to really develop a process recipe. And then we will do data acquisition and system controls to make sure the thing works together. So it's those four areas: is design, analysis, build, and test. That it's those four areas, but the specifics depend on what the customer's looking for and what is their intellectual property.
Okay, so the process is going to vary depending on the client. Are you like recommending materials as well? Are you testing with the different materials? Are you?
Yeah, we're very into the selection of materials, right? And so we do a lot of work in steel, aluminum, a little bit in titanium. Some electrochemical processes that we work with need nickel just because of its chemical resistant properties. We do a lot in plastics. So it just depends on the process, right? So we'll deal with acids, we deal with toxic, we deal with flammable, and then we deal with things where it's like this just needs to be very light. So we're making it out of aluminum or like a titanium.
So based on the requirements of that specific client or project. And are you then like once you do the prototyping stage, will you then implement it within the client's facilities? Do you take it that far, or are you strictly like
Yeah, and it depends on what the client needs, but we do a lot of work inside of shipping containers too. So we'll customize shipping containers. And then we'll install systems inside of those. So these are like energy storage systems, energy generation systems, electrochemical processes. So, like a 20-foot shipping container that has, 20 electrolyzers in them, or a flow battery inside of a shipping container. So, or a CO2 capture system where the entire thing is completely mobile and they can ship it in a 40-foot shipping container to various different environments and test how it behaves in those different environments. So some of those things will go inside of customers' facilities. Sometimes they'll go and they'll ship it to a specific test site that they have, or will operate outside of a plant. Like if there's already an ongoing plant or thermal waste heat that we want to recover and turn into energy, there's already a plant that's there. And if we can have a place for like two 20-foot long shipping containers, we can go and occupy that space. We just need a prepared gravel or concrete, locate those on site. We do others where we do full integration at customer facilities. So, we'll be installing the hardware that we buy. So we've done custom large transformers and inductors and capacitor lines where we'll go and install those at customer facilities. Lots of bus bar work for electrical systems. And we'll have a group of people from our facility that are on site at a customer's facility installing. Usually our installs are in the few week at a time. It's not like we're on site for an entire year. Usually we do as much as we can really here in Spokane where we're located. So that's where our two buildings are. And then we'll integrate as much as we possibly can. So we really are shipping subsystems, and then those subsystems just need to get connected up. So, I'm not sure how many semi-trucks worth of hardware we shipped last year, but I don't know. I would guess it was between, I would guess it's 30, roughly, in terms of semi-trucks that we've shipped of subsystems to customers' facilities last year for integration on site.
Okay. And I know you're growing. I saw LinkedIn
Yeah.
facilities are expanding, so that's super exciting.
Yeah. So building 3 is under construction. So that's gonna double our space. It'll have room for 35 people. So we have 2 buildings right now, right next to each other, 2 different parcels on Trent Avenue in Spokane, which is a fairly, industrial area, but it's just barely out of like the downtown Spokane, but still, 5 or 10 minutes from really everything in Spokane. We have essentially a office, and then there's a clean shop in it. That clean shop is where we do kind of that final integration. That's, where we do actuators, control systems, motors, things where you don't want to have in contact with metal chips and cutting fluid and things like that. And then directly next door is more of a traditional machine shop. So it's a 5,000 square foot machine shop where we have the other capabilities that we use for fabrication and bigger, heavier stuff. Plus, outside of that, we have a yard where, some of the shipping containers get integrated, or the bigger stuff gets integrated out there. We also have space where we can bring those shipping containers inside, because sometimes we'll cut a hole in the roof of it and install a fan in the top of a shipping container, and that's not something where we want outside. And that's just, you don't want it to get rain or snow on it outside. So building 3 will allow us to have, it basically doubles our size of our 2 existing buildings. And then we've got more space for areas in the back, like we can pull a semi, directly through to the back of the shop area. There's a yard out back where we can have a lot more 40-foot shipping containers. Like we're pretty good in terms of like our capability for 20-footers, where we have 3 20-foot shipping containers on site that we're integrating right now that are actually there here today. But when we get a 40-footer on site, it's a lot harder to move the 20-footers around. And so this new location will have a lot more yard space and places where we can, stack multiple 40-footers right next to each other.
Very exciting. Yeah. So I know one of your differentiators is analysis-driven design. And for those who might not be familiar, can you tell us a little bit more about what that means and why it's so critical in reducing risk and ensuring project success?
The analysis-driven design is that our analysis, and this is our physics-based simulations, are very closely coupled to our design. And, most other companies that are doing hardware design similar to this do not have the same type of analysis capabilities that we have. So we use ANSYS. It's really an analyst grade software. It's the same thing we were using to design military and aerospace components. So companies that go and they do design that don't have those kind of capabilities, and sometimes those companies will hire us for our analysis services, right? And so they're kind of designing in a silo, and then they get to where they want it to be, and then they send it over the wall, right, to kind of a different silo for analysis. But we have very closely coupled design and analysis, which means that iteration between those, because we're in control of those two on the projects that we're working on primarily, that means that those design cycles to analysis cycles are very, very quick. For example, if a mechanical designer is working on something and he doesn't know if it's going to be strong enough, right? He can give that to a mechanical engineer or an engineering analyst that we have, and very quickly say, here, this is what this thing is designed for, and we talk about the loads, and then there's quick analysis back and forth, and it's we're talking back and forth on Teams and saying, here's where this thing is experiencing high stress, and and quick suggestions in terms of understanding how we go and we get to a solution that's better, right? And when you're thinking just in terms of design, you're thinking a lot more in terms of how is this going to be very manufacturable? How can we do this in a way that is easy to build a bunch of and easy to integrate and service inside of a system? And analysts and mechanical engineering analysts have different things where they're thinking about, like, how is this going to be strong enough? How is it going to survive those? So we found a way to really marry those together in a very efficient way, to where you're not getting all the way through the design cycle, right? Because some of that last, it's kind of like the 80-20, where that first 80% is quicker and less expensive, and that last 20% is more expensive, right? So we bring that analysis in earlier. And for us, like, just in aerospace, it's like nothing flies until it's analyzed, right? It's kind of the same thing for us, where it's like nothing is really going to go to production if it needs to withstand forces or heat or have to behave in a certain way until it's analyzed, if there's a risk that that's going to cause a failure inside of the system.
Right. So it's a lot of brainstorming, troubleshooting, and verifying, and before you get too far into the process. So yeah,
Early in the system, like prior to manufacturing.
yeah, prior. So there's just that thoroughness I'm hearing that's happening, just to ensure that the product that you're creating is not going to fail, is going to be the quality and meet expectations and parameters. Yeah. Okay. That's great. So if a client comes to you with an idea, let's say a napkin sketches, how do you take that vision and turn it into a functional tested prototype?
Yeah. So our process really starts with trying to understand what the customer's needs are, and then what is that the future state of this device or a machine. And so it's usually a few meetings with the customer, and we get to a point where we understand what the requirements are. And so we'll document what the requirements are, like, hey, this thing has this specific purpose, and it needs to withstand this type of environment, and that environment can be a temperature or resistance to acids, or various different requirements, right? And then we go through and we share what we think it's going to take to do it. So we're very open book in terms of what we believe that it's going to take to complete the project, and I share the entire project estimation spreadsheet that we use with the customer. And so that's kind of a verification step where they say, okay, we want to do this. And I say, well, I get generally very granular in order to give a good price estimate to a customer. So it's going to be like, all right, mechanical engineer is going to spend, a 3 days doing the design of this frame, right? And and the mechanical designer is gonna spend 2 days assembling that frame, right? So we've got it. I mean, it's a very long spreadsheet in terms of it starts in terms of communication, requirements gathering, design engineering, and then analysis, realization, which is creating drawings, interactions with fabricators where, we get feedback from various different outside fabricators on processes, ordering hardware, putting things together, and then starting to test it, and then shipping it to the customer. So it's laying out that entire process, and we make it very visual for our clients, so we can say, this is what we understand you want us to do, right? And sometimes they say, oh, that's great, but let's put a little more in this area. Sometimes they say, let's not worry so much about this portion of it because they've already got some chemical engineer on their team, so we will go and try to fit it into their budget. And then we'll lay out a schedule for how long it's going to take for them to do it.
Okay. So yes, I'm hearing like you have a very organized, thorough process of taking an idea, creating a scope for it, creating a visual, like a representation of exactly what it looks like. So the client is very clear on what or how it's going to work and what they're going to get. And I bet that really cuts down on like the back and forth or having to rework or scope changes, down the road as well.
Yeah, and
Yeah.
scope changes happen, but it's a matter of communicating what the impact of a potential scope change would be, in terms of schedule, scope, and budget. Right? If we do this change, here's the effect, and then really giving the customer a choice if they want to go and proceed with that. A lot of times when we're developing new things, we don't know what that final product is going to look like, and neither does the customer. So there's a lot of discovery that happens along the way, and sometimes you have to change course, right? And sometimes that's a little change. Sometimes it's a bigger change. It just depends on what the discovery is.
Yeah, and I think that's inherent to innovation in general. It comes with the territory. So you have deep expertise in thermal management and two-phase flow. Why are these areas so important in today's engineering landscape?
Yeah. So, keeping processes at the right temperature, or keeping devices at the right temperature is really important for things to act reliably. So, electronics, if they get too hot, really have reduced reliability. Some processes just have to operate at the right temperature in order for them to work correctly. So, we're when we're working with like electrochemical processes where you've got some sort of a feedstock that usually is coming in at something like room temperature, but then it goes into an electrolyzer or like an electrodialysis machine. That you're putting a tremendous amount of electrical power into it at that point, right? And so you want that system to be as efficient as possible. And what is inefficient usually ends up turning from electrical energy into heat energy, and then that has to be managed. And if you don't maintain those components at an adequate temperature, the first thing that you're going to do is continue to get less efficient, and then you get at the risk where you start to risk the things that will melt, right? And these are usually like O-ring seals or plastics that will start to melt. And then you have feedstock, which can be, acidic or a base that's going to be on the ground, and you don't want that. So making sure that things are at the right temperature is very important.
Right.
On the fluid flow side, we experience fluid all the time. We swim, we take showers, we're in air, which is a fluid, right? But fluids can behave in a way that's really counterintuitive. And the only way that, in a lot of times, if you can to make fluid do exactly what you want it to do, is by doing fluid flow analyses. So a lot of the things that we do are like fluid distribution. For example, you've got a tube where fluid is coming in and you want to distribute it very equally to a manifold. And then inside of that manifold, it's going to break into different like electrochemical cells or into different cold plates, right? And so we picture in our brains when we're in the design phase how that fluid is actually going to behave, right? But then it's not until you get it into the tool that we use for this, called computational fluid dynamics, that you can actually really see what's happening. So this is, it's modeling fluid friction, it's interaction with the walls, it's mixing that's happening inside of there. It's modeling the pressure as it travels through these various different places. But then you can actually really understand exactly what's the velocity inside of these channels, how well did I distribute the mass flow rate to each of these different cells, so that these devices are going to act exactly like they're supposed to. Because once you get out of their good range where they're supposed to operate either low or high, those are areas where they're not going to behave like they're supposed to.
Right. So how do you balance creativity and innovation with practical constraints like cost, manufacturability, and timeline?
It's constant creativity in terms of how you are designing things. And it's because it's a lot of blank slate, and we try to go and we fit it into a specific volume, or we fit it into a specific intellectual property area. But it is constant creativity. We do have to guess early on in terms of, we think that it's going to take this much to buy the hardware. It's because we're really, it's a cost of our labor and the cost of the hardware, which is really what drives an invoice to a customer, right? So we can estimate the design cost and that labor rate, but then it's not really until you have a fully detailed bill of materials that contains everything you're going to buy, from the custom components to the screws and O-rings, that what the total system is going to cost. So we design with a schedule or with a cost in mind, and we'll continually look at that and say, okay, we have this much budgeted for these various components. Do we think we're getting over that, right? And sometimes we'll get to a point where we can say, unless we make this process change in terms of how this manufacturing process is going to make this thing, we're not going to hit the price targets. And so we go and we provide alternatives to our customers, and we can say, if we stick with this process, it's going to be cheaper to get to the final design, but then it's going to cost more in design. And there's various different trade-offs, like, hey, we could spend another week or two to go figure this out, and then you're going to save this much when we make it. So it's all about alternatives and providing good alternatives to our customers, because really we want to provide them with solutions, right? So we want to, if we run into a design challenge, then we need to come up with a way to creatively solve that problem to give them options.
Mm-hmm. Right. And tell me a little bit about the role of simulation tools then in that process.
Yep. So if we find something that is heavy and it's strong, a lot of times over designed, right? We can use like structural analysis. If there's a big heavy frame, that's it's the cost of the materials when it gets made, and then every time and the labor to do it. So every time a customer then goes and buys this frame, they pay for all of those materials again, and they pay for all of the labor to build that over engineered frame. The alternative that we offer is you can do physics-based simulation, so structural analysis, and you can say, okay, here's the existing frame. And if we spend a week of design or 2 weeks or whatever it turns out to be and go optimize that design, then we're taking material out of it. So if you think about the cost of steel or aluminum on a per pound basis, let's say we take out 30% of the weight of that frame, then you roughly are taking about 30% of the cost of those materials. But it's also the manufacturing labor, right? So if we can optimize that process and maybe change the way that those joints are designed, or replace one component with the other, or just kind of change the concept of how this thing is going to carry that weight, then we can save money on the labor every time you build it. So it's like you buy once, cry once, you pay for that labor at the beginning to do the analysis and improve the design, but then you're not paying for it every single time you make that.
Makes sense, yeah. So working in a variety of industries like you do, from carbon capture and renewable energy to aerospace and biotech, what trends or technologies do you think will have the biggest impact in the next decade?
I think that the biggest impact is going to be energy. So we're headed for, I think, an energy crisis in terms of supply versus demand. And that's a trend that the utilities, trade groups have been identifying for years. In Washington, at the end of this year, we're going to be shutting down our last coal-fired plant. And the likelihood of having rolling brownouts is going to be massively increased. Plus, we have a huge increase of data centers, especially supporting AI. And I think that is going to be just increasingly part of the world where there's an increasing energy demand. We need to increase our ability to generate energy and to store energy. Solar is awesome, but then the sun sets, right? So you have a great way to generate clean energy, and the wind generally will follow the heat of the sun. And so the wind will decrease at night too. So during the nighttime, we need a way to store that energy. And so we need things like batteries and flow batteries and various all kinds of different ways to store energy. So I think the biggest impact that we can have right now is to have adequate energy supply in a manner that's clean and non-polluting. And I think that there's a lot of rewards short term for clean energy, and also that because it's not dirty, polluting. Even our cleaner coal plants have pollution, and burning fossil fuels, even clean and efficient ways, still have pollution, but also from carbon dioxide out into the atmosphere. So, we can do a lot also in carbon dioxide, and hopefully slow our warming by capturing carbon. I think that one of the most promising would be capturing it directly at the source. We have a local company, Carbon Quest in Spokane, that captures it directly at the source, at like boiler exhaust stacks. But we're working with multiple other carbon capture companies that are capturing it in various different ways. Capturing it directly out of the air, direct air capture, is something that we'll need to basically reduce the total level of atmospheric CO2. And then I think the third is really switching over to a more hydrogen-based economy to replace fossil fuels. So if we can use renewable energy to split water into hydrogen and oxygen, and then we can use hydrogen for a lot of our infrastructure and our transportation, and for energy storage, right? So we can then recover that energy in hydrogen back through a fuel cell, which then cleanly produces electricity and your output is essentially water, or you can burn hydrogen and then the combustion of hydrogen is not creating CO2. So there's some real good options that we have where we can create and store energy in a better way and use an energy carrier like hydrogen instead of gasoline or diesel to power our economy, and then kind of put a Band-Aid on our previous carbon release from burning fossil fuels by doing some carbon capture.
Yeah, so I see that too, and talking to other leaders in the space, just the focus really is on creating that clean, renewable, sustainable sources of energy. And like you said, because of the increasing needs with the AI and data centers, yeah, I see that. So Johnston Engineering places a lot of emphasis on integrity, excellence, and continual improvement. How do these values show up in your day-to-day work with clients?
Yeah, so you're talking about our core values as our company. So right from the integrity standpoint, that means that we're honest in all of our work and in all of our interactions with our clients. It is providing really our services in a way where we do the best that we possibly can, and we spend our money. We spend the client's money like it was our money in a way that we think is in their very best interest. And it's what they tell us their best interest is, right? So they tell us and we try to do it, but it's being honest in all practices. The continual improvement is that we're always trying to get better. This is as a company, as individuals at the company. So we have improvements that we're working on in the company. So we're in the process of being ISO 9001 compliant. So that's writing a lot of processes. That's making sure that we're documenting how we do design modeling, documenting how we do drawings. It's documenting all of our processes all the way out through shipping to our client. That is really making sure that we provide them with a consistent, repeatable product, right? And our product can be engineering design, it can be or physical hardware, or analysis results. So being consistent with that, and even our employees on their development plans, they have specific things that they're supposed to be doing every year to improve themselves. So this might be you take a class in a particular type of design or a particular type of analysis. So everybody has time. Like everybody's got their billable goals that they have for the year, but they also have time that's dedicated for their own personal improvement. And there's time that's dedicated for everyone for a internal process improvement. And then so we'll have engineers that are presenting in front of the company for a process improvement. And this can be, hey, here's how to do a better job of calling out weld symbols on your drawings, or here's a better way to track budget when we're having our weekly customer meetings. And then the third is that we're always do your best work. So this is, you're focused, you're ready to work every day. You're really putting in your very best work for the customer all the time. So yeah, that's really our values as a company. And so as we put all of those together, we're trying to give our customer really the absolute best that we possibly can with their intents really in our heart, and to make sure that we're very truthful, and we're trying to be better internally, and we're trying to really even help the customer be better all the time too.
Yeah. So practicing with integrity, just really treating a client how you would want to be treated yourself, and always being sharp and learning and making sure that you're up to date with the latest and greatest information, and just moving forward responsibly and doing your very best every day, and just hold that accountability is great things to live by. And finally, for our listeners, what advice would you give to inventors, entrepreneurs, or companies that have a promising idea but aren't sure how to move into successful production?
Yeah. So I would say that you need a team because most people who are inventing things will have a skill set, right? And a lot of them are very creative. and they'll be good at their thing that helped create that idea, but they probably need a team. So, we're part of that team where we can help really develop the idea farther. But you also need you need patent attorneys, right, to make sure that nobody else has a protection for the intellectual property that you're trying to bring to market. You need help on the business side. So you need, we have a business coach that we use and we pay for that is really great for us. And I would suggest that of anybody who is in a situation where they're trying to launch a business and trying to really bring a product to market. It's a long road, and you go as fast as you can would probably be the biggest advice, because you've got an idea to solve a problem, and if it is a big enough problem, there's other people working on solving that problem too, and they might be coming at it from a completely different method. They might have completely different intellectual property to solve that, but if it's a big problem, you're in a race, right? And you need to go and go all in and understand what it's going to take to do that, right? So it might be bootstrapping to get it moving, and then going and trying to raise money and go get some initial seed money to go do that and build a prototype. But eventually it's going to have to get to that next stage where you need to go and raise, a Series A round of funding, and how you go and do that, and getting help on the business side and the legal side for how to do that. And you got to think big, right? How am I going to get to this point where this is going to be, where my technology idea is going to be relevant in the market? And how do you go to get to the point where you have that device out there, or that machine out there, where you can be profitable?
Yeah. I think that's some great advice. And I've heard that before too. Like, don't worry about being perfect. Speed is more important. Just get it out there, and you can perfect it later. Just get your idea out there.
You don't want your device to go and be a Swiss Army knife where you've got a knife and some scissors and a toothpick that are all kind of like, okay. Focus on being like the very best toothpick out there.
Yeah. Well, Andy, it's been great learning about your journey, your innovations, what's coming out of the new, what's new for Johnston Engineering, and how your team's expertise is helping clients across various industries. So thank you so much for sharing your story with us today. And for our listeners, where can you learn more about Johnston Engineering?
Yeah, sure. So you can find us at Johnston PE, so Johnston PE, as in professionalengineer.com. There's a contact form there. There's a phone number there for us. You can learn about our projects, our services, and ways that we can hopefully work with you. So yeah, we like to talk to people with ideas, and really get them from the scale of even very beginning concept napkin stage up to being out a real device out in the market. So feel free to reach out. Don't be shy. We're used to talking to people who are very early in that stage, or even mid stage, and want to scale up. So we're happy to talk with you, give you advice, even if it doesn't turn into a job for us. We like to talk about new developments and people's ideas. So yeah, feel free to reach out.
Great. Well, thank you again. And this has been Industry Ignited, where we spark conversations that move industry forward. Thank you.